Good morning, everyone. A very good morning to all of you. Welcome to Geeks for Geeks. So let's continue our discussion on network analysis, Maha Revision Part 2. So today's class, we will be discussing the revision of transients and AC analysis. So these are, just a minute. चलो. So आज के क्लास में transients और AC analysis. To last lecture we have completed the basics, network theorems and two-port network. So today let's quickly revise the things of transients and AC analysis. Okay, so this is about myself. I hope you people know me, but still these are my credentials, and you can scan this QR code and join our Telegram channel where you can get the regular updates and whatever the notes possible in our Telegram channel. So the after this particular series, the day after tomorrow, we will be starting the PYQ series. I will be starting the digital circuits, and इसके बाद control systems अंकुर सर शुरू करेगा, and all other subjects will follow. Okay, so I hope you people are attending this exam. Today also there is an exam for this Geeks per Geeks gate before the gate. So let's start without any further delay. So first, the topic of our discussion now is transients. Okay. Good morning once again, everyone. So the topic of our discussion today is transients. So what are transients? Let us have an understanding. Um, because it's a quick revision, I will try to wrap up in 2 hours the total transients. The total transients, let me give a try to finish it off in 2 hours. So firstly, what are transient? Transient means suppose all of a sudden we have applied some source to the network or removed the source from the network. All of a sudden I have applied some source to the network or removed the source from the network. That is, all of a sudden energy is applied or removed from the network, then network will suffer from some sort of instability. For some time, it will require some time to change its state of mind. Suppose up to 8 a.m. you are not in the class, suddenly class was started. Then what happens? Your mind will require some time to tune up. That's why initially we will have introduction. We will discuss today, good morning, everything, right? That is to settle down your mind. Same way, network also requires some time to settle down to the final value. This is what we call transientary period. For example, you can see here. So you are happily sleeping. Suddenly, alarm rings. Then you are in a disturbed mode. This disturbed mode is called transientary period. This disturbed mode is called as transientary period. After this disturbance, you start working. This working is again steady state. This working is again steady state. ठीक है, मिथुन कर सकते, कोई दिक्कत नहीं. ठीक है, चलो. So similarly, you are in one state. You want to change your state from sitting to standing. In between, always, suppose you are happily sitting, I ask you to stand up. You require some time to stand up, right? So this particular transition period is what we call transientary period. The same happens with your electrical networks also. So why it is required? For example, let's take this example. Say there is a firefighting system. Suddenly fire has happened. Suddenly fire has happened. Then there is a detector here which will be detecting the fire, and immediately water should be sprinkled and it should stop. Water should be sprinkled and cool the system. Okay, stop the fire. But what happens is when it has detected, there might be some solenoid valve inside, there might be some relay or inductor, whatever may be. It requires some time to detect and give the water. In between time is what we call transientary. In this kind of crucial application, even 1 second delay is also costlier. So that's why we should know how much time your system is really requiring to give you the response. How much time your system is requiring to give you the response. This is what we call transientary period. So, and also sometimes what happens during transient period, how it is behaving, it is also important. So based on your requirement, we should know how much time it requires to reach the steady state, and during transient how it is behaving. Is it damaging the system? That maybe it is giving some impulse during the transient period, Is it safe for my system? Considering all these conditions, not only steady state response, we should also analyze the transientary behavior of the system. Okay. So transients क्यों होता है? Why transients will occur? Network के अंदर, inside the network, we have three kind of elements: resistor, inductor, capacitor. Resistor voltage current relationship is given by V equal to IR. It is not dependent on time, so it can change its values instantaneously. What is the meaning of instantaneously? I will explain. For example, in the entire transient, remember this part. Say, generally, in our transient terminology, 0 is the point where switching action takes place. All of a sudden, you are closing the switch or opening the switch. That point of instant is what we call 0. Just before the switching action is 0 minus, and after the switching action, we call it as 0 plus. Just before, that is just before your alarm rings, you are in happily deep sleep. That particular time is what we call 0 minus. So what is 0 minus? It is 0 point minus 0 point not 1. What is 0 plus? It is plus 0 point not. The difference between 0 plus and 0 minus is 0.000002, which is almost equal to 0. We call the time difference between these 2 points is called instantaneously, or within 0 time. This is infinity minus infinity. Got it? Right. Chalo. Now, listen here. Listen here. So this is the terminology we will follow. What is minus infinity? A long time before switching action. 0 is the point where you are operating the switch. You may be closing, you may be opening, whatever may be. Physically, the point where you are operating the switch is the point called as 0. And infinity is a long time after the switching action. A long time after the switching action. That is, for a long time, if circuit is undisturbed, then it is called as steady state condition, infinity. Chalo. Now you can see, if you have resistor voltage V equal to IR, there will not be any transient. But if you have inductor capacitor, they don't change its energy all of a sudden because of their own natural behavior. They cannot change its values all of a sudden. They cannot change, the inductor capacitor cannot accept the sudden changes. Because of this, what happens is, all of a sudden, if you want to give energy to the network or remove energy from the network, inductor capacitor will be opposing. Because of this opposition, there will be transients in the response. Because of this opposition, there will be transients in the response. You can see here. Suppose this is my network. At time t equal to 0, you may be closing the switch or opening the switch, the point at which we are operating the switch. So all of a sudden you are giving some energy or removing energy from the network. Inductor suddenly it cannot become 0. Suddenly it cannot reach to that value. Capacitor also. Because of this, you will be having transient response, because the current in the inductor is given by 1 by L integral V dt, where energy in the inductor is depending on current half L I squared. Similarly, voltage across the capacitor is also depending on integration only. Integration cannot give you sudden changes. Capacitor energy is equal to half C V squared. Got it? Right. So, if the network contains all this story I have explained you right now, energy present in the memory elements due to integral dependence cannot change all of a sudden. So, what happens? Network contains only resistor, no transient, inductor capacitor present, there will be transientary response. Now, before going for transient analysis equations, we should also have the basics of inductor and capacitor. Quickly we will revise, not like a regular class. This topic itself I will teach for half an hour, and the inductor capacitor basics itself take 2 hours. But here in 2 hours we will finish entire transient. So there is a difference. Normally I will take around 20 hours comprehensive course. I will take 20 hours to discuss the transient. So now see here, the inductor and capacitor at time t equal to 0 plus and infinity means immediately after switching action and long time after the switching action, how the capacitor and inductor will be behaving. Okay. If you take inductor, uh, ZL is equal to SL or J omega L. If you take time t equal to 0 plus, this analysis is not mathematically correct, but still I will use it for a shortcut to remember easily. At time t equal to 0 plus, inductor omega equal to infinity, if you take, impedance will be infinity, or you can take it as an open circuit. Capacitor ZC will be 1 upon SC, 1 by J omega C, 1 upon J infinity, 1 by infinity is 0, short circuit. Okay. So immediately after switching action, please remember inductor acts as a open circuit, capacitor acts as a short circuit. Similarly, at time t equal to infinity, omega equal to 1 upon infinity, that is 0. It is like a DC condition, steady state condition. Inductor will be J omega L J0. So inductor acts as a short circuit. Capacitor 1 upon SC, 1 by J omega C, 1 by J0. 1 by 0 is infinity, means open circuit. Got it? So steady state, inductor acts as a short, capacitor acts as a open circuit for DC excitation. For DC excitation at steady state, inductor acts as a short circuit, capacitor acts as a open circuit. Is it clear up to this? Okay, just give me a moment. Now, I told this analysis is wrong. Why? Because 0 is instantaneous time, omega is 2 pi by time period. So I should not relate this instantaneous time here. This is just for your what we call easy remembrance only. Here also, here it is okay. Omega equal to 0 is logically correct for DC. Okay, but still we should not use the time here because omega is 2 pi by time period, not instantaneous time. But here you can also say a time t equal to 0 plus means immediately after switching action, sudden change means very high frequency of the change. Mathematically, we can prove these conditions like inductor current equation or capacitor voltage equations. We can prove it. I'm not going through that. Now see here. What is the meaning of steady state? Steady state, I told steady state inductor is a short, capacitor is a open. So these conditions are very, 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 very important throughout the end of the transients. If you want to understand transient, if you want to solve any problem using transient, compulsory you should know these what we call uh, these conditions you should remember. You should not confuse. 0 plus inductor open, capacitor short. Infinity inductor short, capacitor open for DC excitation. That's it. You should remember like anything. Whenever any problem comes, we need to apply them. So let's move here. I have an independent source. What is the meaning of steady state? If you have an independent source connected to the network for a long time, we have not disturbed the network. Then whenever the examiner use long time, it means you are in steady state. For a long time, if the network is undisturbed, independent source is connected to the network for a long time, then the network is in which state? Steady state. Network is in steady state. At steady state, inductor acts as a short circuit, capacitor acts as a open circuit. But originally, what is the meaning of steady state is energy in the network will reach its final value. At steady state, what happens? The energy present in the network will reach its final value. Suppose if it is charging, it will charge to the peak and it will not further charge. That is steady state. Suppose it is discharging, it has discharged fully, not further discharge possible. That is what we call steady state condition. So ideally you should wait up to infinity, but you cannot wait up to infinity. Practically 99.99% of the transients will be die by the time t equal to 5 tau. Time t equal to 5 tau. That's why we take 5 tau as the steady state, where tau is the time constant. You can see here For example, you take inductor. What I told, energy is equal to half L I square will be constant at steady state, right? You may apply the source or remove the source. Maybe it is reaching highest value or zeroest value. Okay, zeroth value. So if it is constant, here L is already a constant, so IL must be a constant. Then what is DIL by dt? D by dt of constant, 0. What is LDI by dt? Is 0. That is equal to voltage across the inductor is 0. Voltage across the inductor is 0 means short circuit. That is the reason we treat inductor. This is also one way we can say inductor is a short circuit at steady state. Similarly, capacitor you take of CV square. Okay, so this is constant. So VC will be equal to constant. Then what is dVC by dt? If VC is a constant, then dVC by dt will be d by dt of constant. What is d by dt of constant? 0. C dVC by dt is 0. Current in the capacitor, 0. Current 0 means open circuit. Okay. So at steady state, inductor acts as a short, capacitor acts as a open for DC excitation, which is what we have discussed in the last part, which is proved again here. So let's move further. So let us see the current and voltage equations of inductors. What is the current equation in the inductor? IL of t is 1 by L integral minus infinite to t voltage across the inductor VL of t dt. So 1 by L minus infinite up to 0 minus VL of t dt. Okay, I am splitting this integration, and 0 minus to t VL of t dt. Now substitute time t equal to 0 plus. What is your IL of t? 1 by L integral minus infinity to 0 minus VL of t dt. 1 by L 0 minus to t equal to 0 plus. So up to 0 minus, this part will give you inductor initial current is the total current 0 plus. And you can see here, I told you what is the difference between 0 minus and 0 plus. 0 minus and 0 plus, the gap is very minimal, point not 2, which is almost equal to 0. So the area under 0 minus to 0 plus is almost equal to 0. Almost equal to 0 for any practically existing input. So my IL of 0 plus equal to IL of 0 minus. Very strong point here is inductor current cannot change instantaneously. Inductor current cannot change instantaneously. Similarly, energy in the inductor EL of 0 plus is always equal to EL of 0 minus. EL of 0 plus is always equal to EL of 0 minus. Here, current at 0 plus is previous value plus 0. Current 0 means open circuit. That's why at time t equal to 0 plus, what is the equivalent for the inductor is its initial current parallel with a open circuit. Initial current parallel with a open circuit. That is the reason at time t equal to 0 plus, we are replacing inductor with a open circuit. Originally speaking, we are taking it as 0, but mathematically 0 minus to 0 plus is very negligible. It is not exactly 0. Over a period of time, if you add these values, you will get some value here appreciably, and you will get the change in the current. But 0 minus to 0 plus, it is almost very got it. So now let's move further. Is it clear up to this? If you have any kind of queries, feel free to ask me at any instant of time. You can stop, ask the doubts. I am very happy to help you. So up to now, we are just discussing the basics of inductor, capacitor, because those are very important to understand your transient. To understand your transient, they are very important, very crucial. Okay. Chalo. Let's move. Suppose I said inductor current cannot change instantaneously. Suppose you are sleeping. If I want to wake you up, you said I cannot wake up immediately. I require some time, 5 minutes, 10 minutes. Same happens with inductor. But is it true every time? Suppose I do this job. Uh, I just bring a bucket of water and throw it on your face. In that case, what happens? You immediately wake up, right? You immediately wake up and sit. Same happens with the inductor also. It cannot change instantaneously for any practically existing input, but there is an input called impulse. There is an input called impulse, which exists only at time t equal to 0. Okay. So see here. If VL of t equal to del of t. What is the meaning of del of t? Impulse. What is impulse? It will exist only at 0. It will not exist before 0, after 0. What is the area under the impulse will be equal to 1. That basic you should know. So I replace here so VL of t equal to del of t. Okay. Then what happens at time t equal to 0 plus? Up to 0 minus, what is the area under the impulse? 0. 0 minus to 0 plus, what is the area? 1. So what do you get here? In this case, IL of 0 minus is 0, but IL of 0 plus will be 1 by L. So here inductor current can change instantaneously. Inductor current can change instantaneously. Up to 0 it is 0, after 0 it will be equal to 1 by L. Inductor current can change instantaneously. Same way here also, EL of 0 plus, EL of 0 minus equal to 0. But 0 plus is a half L square, you get 1 by 2 L joules. So final conclusion is like this. Inductor current cannot change instantaneously for any practically existing input, but it can change for impulse voltage as excitation. When do you get impulse voltage is if you apply, if there is a violation of KVL or KCL, in that case, impulse will happen. When there is a violation of KCL or KVL, you will get impulse in your response. Now, same rule is applicable for capacitor also, 1 by C integral minus infinite to t current IC of t dt. So what is VC of 0 plus? Same story you can write 0 minus to 0 plus IC of t dt. So this part will give you VC of 0 plus and this part will give you 0. So similarly EC of 0 plus equal to EC of 0 minus. And capacitor voltage 0 means we should replace it with a short circuit. Voltage 0, short. And that's why at t is equal to 0 plus, capacitor acts as a short circuit with initial voltage. Similarly here, if IC of t equal to del of t, in that case what happens? So VC of 0 plus equal to 1 by C. And same like previous case, I am not analyzing everything here. So what is the final conclusion? Capacitor voltage generally cannot change instantaneously. VC of 0 plus is equal to VC of 0 minus, but it can change for impulse voltage, impulse current as excitation, impulse current as excitation. Similarly, its energy also. Similarly, its energy also. Okay. Capacitor voltage cannot change instantaneously for all practically existing inputs. Similarly, its energy also, it can change for impulse current as excitation. So if there is a violation of KVL like voltage source short circuit, anything, two different voltages connected in parallel, there is a impulse current. Violation of KCL, there will be impulse voltage. For example, see here. For example, you have a resistor, a capacitor connected in parallel across a voltage source at time t equal to 0. Okay. So now see here. At time t equal to 0 plus. What is the meaning of 0 plus? Immediately after switching action. Capacitor acts like a short circuit is what we discussed. Now we have a voltage source parallel with a short circuit V by 0 infinite current. So this is what we call violation of KVL. In this case, impulse current occurs. But practically this will not happen because it will have some resistors. Internal resistance will be present. Okay. Suppose if this resistor is in series, this problem will not happen. So like this, whenever there is a violation of KVL, impulse will occur and capacitor will charge instantaneously. Sudden change can happen for the capacitor voltage. Now see here, the next important topic, very important to understand in any transient question, we should use this compulsory, that is equivalent circuits. Any transient, we should compulsory use the concept of equivalent circuits. Let's discuss that. Okay, chalo. Now let us draw the equivalent circuits. Suppose you have an inductor. I'm not proving that because it will take, I'm not going to the proofs, it will take a lot of time. In the available time, we need to quickly revise everything. Suppose I have an inductor with some initial current I naught. Okay. So what is the equivalent for this? This is the inductor equivalent practically for all t greater than equal to 0. For all t greater than equal to 0, this is the practical equivalent of the inductor. Here, different possibilities. Substitute time t equal to 0 plus and time t equal to 0 plus inductor acts as what? Open circuit. So, IL of 0 plus equal to IL of 0 minus plus 0. Perfectly represented or not? I naught is initial value, inductor is open circuited. Okay. Here, if I naught is 0, I naught can be any value. Suppose मैंने I naught को 0 किया. For example, my I naught is equal to 0. Initially कोई current नहीं inductor पे. Initially there is no current in the inductor. In that case, what happens? We replace inductor with a open circuit. Okay. Right. Now, similarly, at time t equal to infinity, Time t equal to infinity, whether you have I naught or not, final value will never depend on the initial value. We should replace inductor with a short circuit. Why I am explaining everything? Because these are the circuits which we use in our networks compulsory. So we should understand. These are the three figures. Whenever any RL circuit, any inductor circuit comes into picture, we should replace our network with any of these three. That's why I'm stretching more on this. Okay. Then there is another equivalent called Laplace equivalent of the inductor. Laplace equivalent of the inductor is replacing L with SL ohms, inductor current with I naught by S, IL of S, VL of S. Okay. So this will be, what is the Laplace transform of this one? Multiply them. I mean, current source parallel with the impedance, multiply them, you get Li naught as the source, arrow direction negative to positive, series with SL. So these are the Laplace equivalent. So say this slide is for any transient problem, we should use them according to the time t equal to 0 plus or steady state. According to the condition, we should use any one of them. Please understand, steady state value always short circuit. We never depend on the initial value. Initial value can be anything. Steady state, we should replace inductor with a short circuit. Thank you, Vishnu. Chalo, let's move. So same analysis, let me do it for capacitor. Okay, let me do it for capacitor. Capacitor equivalent will be voltage source V naught in series with capacitance C. The current will be IC of V. Okay, so this is the capacitor equivalent. Now here also three possibilities we should take. What are those three possibilities? What is the equivalent at time t equal to 0 plus? T equal to 0 plus, uh, what if V naught equal to 0? And also t equal to infinity, steady state. So already I told this condition, if possible, can you recollect? T equal to 0 plus, capacitor acts as open circuit or short circuit? T equal to 0 plus, capacitor acts as a short circuit. T equal to infinity, capacitor acts as a open circuit. T equal to 0 plus, capacitor acts as a short. T equal to infinity, capacitor acts as a open. So you can see here, Vc of 0 plus equal to Vc of 0 minus plus 0. That plus 0 is replaced with a short. If no initial value, simply short circuit. Steady state, whether initial value is present or not, always we replace capacitor with a open circuit. And this is the Laplace equivalent. V naught by S series with 1 upon SC, Vc of S and IC of S. And what is the equivalent here? 1 upon SC ohms here why by S? Because V naught for t greater than equal to 0, V naught into U of t, V naught into 1 by S. So if you take this with divide with this, you will get CV naught parallel with 1 by SC. CV naught parallel with 1 by SC. Current source transformation I have applied. These are the Laplace equivalents and this is the time domain equivalent. So that finishes the basics of inductor and capacitor. We discussed at 0 plus and infinity how inductor and capacitor acts, and steady state meaning we have discussed, and also initial 0 minus 0 plus how inductor current capacitor voltage will be changing, and also we have discussed this uh, equivalent circuits of inductor and capacitor. Now we will be moving for the application of this circuits, this whatever we have discussed, this basic under three different cases of what we call the transientary conditions. There are three different possibilities, are three different cases where the transient questions can be asked. Suppose all of a sudden your network is having independent source working for a long time. That is my network. Suppose a fan, पंखा है, पंखा चल रहा है बहुत समय से, suddenly मैंने इनको बंद किया. The fan is running for a long time. Suddenly I switch off that. Then what happens? This is one possible condition. दूसरा possibility क्या होता है? What is the other possibility? The fan is in the off condition. Suddenly I came and turn it on. So another possibility you can have is I analyze what is the fan speed initially and finally. So these three kind of problems can appear. What are they? Source is present in the network for a long time and network is in steady state. The response is in the steady state. Suddenly I remove the source. इसको बोलते source free circuit. Another possibility is source is given. We may be able to, we are finding initial and final values. And last possibility is source is applied. What is the response from 0 to infinity? So fan is switch on, how the fan is changing its speed and reaching steady state and how it is behaving for the total time period is what we call the third case. Network with sources and total response to be evaluated. All these three cases we will be discussing one by one. Okay. Chalo, shall we proceed? Right. First case. Source free circuits. In the source free circuits, mm, what is the meaning of source free circuits? It is after switching action, independent source removed from the network. After switching action, independent source is removed from the network. So here what happens? Here, first possibility is RL. Second possibility is RC. Third possibility is RLC. RLC comes under second order. We will discuss a little later. Now, whether it is RL, RC or RLC, in all these cases, what happens is resistor will not store any energy. Resistor will not store any energy, but inductor capacitor will be having stored energy. So all of a sudden, if you remove the source from the network, then what happens is this inductor and capacitor will be having some stored energy. Resistor is not having any stored energy, but resistor is hungry to eat this energy. So the energy present in the inductor will be taken by resistor. Capacitor will be taken by resistor. LC will be taken by the resistor. LC will be taken by the resistor. So what happens here in all these three cases? The energy present, means stored energy present in the inductor capacitor will be given to resistor. Steady state energy present in the network is equal to 0. Steady state energy present in the network is equal to 0. In all source free circuits, energy present in the inductor capacitor will be given to resistor. Steady state energy present in the network is equal to 0. This is the first case, source free circuits. Okay, in the source free circuits, let's do the analysis how the response in the RL circuit, how the response in the RC circuits, everything. For RL circuit, I'm not deriving it. Say this is the condition. I have a resistor and I have an inductor with some initial current. So no source is present. Okay, in this case, what happens is by KVL, minus VL minus VR equal to 0. So minus L di by dt minus R into I of t equal to 0. So di by dt plus R by L into I of t equal to 0. Now, if you further solve it, finally, what do you get? I of t equal to I naught e power minus t by tau. This is the source-free RL circuit response, where tau is equal to L by R or L equivalent by R equivalent. Units are in seconds. So this is the response of source-free RL circuit. What is the voltage across the inductor formula? L dIL by dt. So L into d by dt of this one, I naught e power minus t by tau minus tau. Tau is equal to how much? So minus R equivalent into I naught e power minus t. Okay, right. Energy in the inductor EL of t, half Li square. So half into L into I square, which is I naught e power minus t square will give you 2t, right, by tau. So this I will replace with E naught e power minus t by tau by 2 will be represented as tau. So tau E equal to tau by 2. So generally the energy in the energy time constant is less than the total time constant. Energy time constant is less than the time constant of current and voltage. Generally time constant of the network means we speak about current and voltage. Why? Because energy decays faster, or energy will reach steady state little early compared to voltage and current. So overall network will reach steady state means we should consider which one when everything becomes almost zero, right? So that happens after when inductor voltage or current will reach zero, because it takes more time. So you can see the response will be exponentially decaying, means like this. If you take this is the current IL of t, which is exponentially decaying, and we can 5 tau. Suppose you start at I naught. Okay. At time t equal to 5 tau, tau cancel, e power minus 5 will give you 0.002 I naught, almost equal to 0. Okay, that is the reason we take 5 tau as the steady state. 99.9% of your transients will be died by the time t equal to 5 tau. In control systems, you may take 3 tau also, because there 96% of the transients will be died. 4 tau, 98% of the transients will be died. That is, if you take here, for example, tau, you get 0.368 into I naught. At 2 tau, you get 0.13. 3 tau, you get 0.04. That is almost 96% of the transients. Depending on your system requirement, you may take 3 tau. Sometimes you take 4 tau. In networks, as a standard, we take 5 tau. In digital circuits, in ADC and DAC, sometimes we may take more than 5 tau also, because there, how much is this point, this much is available now. So is it okay or not? It depends on step size of the system. So if the quantization we cover, if it is less than step size, we can take 5 tau as the steady state. If it is more than step size, we may take further time also for steady state. It depends on application, but in a generalized way, for networks, 5 tau is the steady state condition. 5 tau is the steady state condition. Okay. So is it clear up to now? Shall we proceed further? I will give you the same analysis for RC also. Okay. Chalo, let's move the same analysis. Let me do the same analysis for the RC circuit. Let me do the same or similar analysis for the RC circuit. So for RC circuit, same way the equation will be Vc of t equal to V naught e power minus t by tau for t greater than equal to 0, where tau is equal to R equivalent into C equivalent. Inductor and capacitor always dual to each other. The analysis there for current, here for voltage, like that. Okay. So here current in the capacitor is equal to C dVc by dt. You do this C dVc by dt to this equation, you get minus V naught by R equivalent into e power minus t by tau. Here why it is coming negative means, because I will tell you. Suppose you take a capacitor. When it is charging, the current direction will be positive to negative. But in the source-free circuits, what happens? Source is removed. When source is removed, who will give the energy to the resistor for temporary period of time? During this period, capacitor is discharging. When it is discharging, it is delivering the energy. When it is delivering the energy, current direction will be reversed from negative to positive. Because of this, you get minus in the source-free circuit. Same way, inductor voltage also you got it negative in the source-free circuits. VL of t equal to minus V naught by RL e power minus t by tau. Okay. Now, what is the energy in the capacitor EC of t? Of C Vc square of t. Of C into V naught square e power minus 2t by tau. Okay. Where tau E is equal to tau by tau. Okay, this is for energy, current and voltage equation of RC circuit. Here, let's have one important discussion. What is the time constant of inductor? L by R. What is the time constant of capacitor? RC. So, L by R square C is not having any units. We can say dimensionless. Because L by R is also seconds, RC is also seconds. So, sometimes they ask you, what are the units of L by R square? It is farad. What are the units of R square into C? Henry. Okay, sometimes they ask you this kind of questions. What are the units? So L by R also seconds, RC also seconds. They L by R square C, no units are dimensionless. Got it? Chalo. Now, RLC circuit is a second order case. Generally, the response for RLC we evaluate by Laplace transform approach. We will see with some examples little later. So that is about your source-free circuits. So let us have one solution, one problem and solve it. Yeah, please read this question. Try to understand. Very good. So let's solve this question and we'll apply whatever we have discussed till now. Whatever we have discussed till now, let's try to apply it here. I have a circuit with 8 and what we call 5 ampere, 8 ohms, and switch is moved from position 1 to 2 at time t equal to 0. Then I need to find the current in the inductor for t greater than equal to 0. So assume switch is at position 1 for long time and move to position at time t equal to 0. At time t equal to 0, assume my switch is moved from at this location to this location. Okay. So let us give a try here. So long, whenever examiner use the term long time, what does it mean? Up to 0, my network is connected here means for a long time network is undisturbed. So before 0, before switching action, my network is in steady state. Before switching action, my network is in which state? Steady state condition. So see here. At time t equal to 0 minus, independent source is connected to the network for a long time. Network is undisturbed. So which state network is in steady state? So this is my circuit. 5. In any transient question, it is always very important to identify before switching action. Always note inductor current and capacitor voltage. Why should we note it, sir? Because inductor current, capacitor voltage, next value is depending on the previous value. They cannot change instantaneously. IL of 0 plus equal to IL of 0 minus, VC of 0 plus equal to VC of 0 minus. So compulsory, if you have two inductors or two capacitors, any number of elements you have, for inductor, note the current value, capacitor, note the voltage value before switching action. So at time t equal to 0 minus, network is in steady state. Replace inductor with a short circuit. This is IL of 0 minus. So what is IL of 0 minus? Total current into opposite resistance by total resistance. 4. Okay. IL of 0 minus is equal to IL of 0 plus. Now, for t greater than equal to 0, what happens? For t greater than equal to 0, the switch is moved from position 1 to position 2. So source is removed from the network. So this part will not have, this is the equivalent, right? I move this switch to this position. So this source is disconnected, only this part will be available with me. I can replace, what is the inductor equivalent? Initial current I naught parallel with the inductance. Inductance is how much? 3 Henry. I naught is how much? 4. Now for this circuit, what is L equivalent? 3. R equivalent 14. Tau L equivalent by R equivalent. Then what is your IL of t? I naught e power minus t by 2. If you want, you can also find VL of t minus R equivalent into LdA by dt. So this is how you can find the response in the RL circuit. So after switching action, sometimes they ask you what is the response at 0 plus. If you want, you can just draw this circuit at 0 plus. You replace inductor with a open circuit. Okay. At 0 minus, short circuit I made it. Suppose same question asked at 0 plus, replace inductor with a open circuit, because it is always important equivalent circuits. If examiner asks you what is 0 plus response, replace in that case inductor with a open circuit. Like this. Okay. So please understand, only inductor current cannot change instantaneously. You see IL of 0 minus will be 4, IL of 0 plus. But inductor voltage will change instantaneously. Resistor current and voltage will change instantaneously. Otherwise, KCL, KVL will not get satisfied. Because 0 minus, suppose here some in this resistor some current is there. 0 plus, once you change the switch position, its current will become 5 ampere. Earlier it is 1 ampere. Now it will become 5 ampere. Why? Because otherwise KCL will be violated. So resistor current voltage will change instantaneously. Inductor voltage will change instantaneously. Only inductor current cannot change instantaneously. Only inductor current cannot change instantaneously. Shall we proceed further, guys? Is it clear with total problem? You have any kind of query, feel free to ask me. Otherwise, I will move for the next question. Or I will give you the next question. I want you people to answer it. Just based on what we have discussed. Okay. Chalo, let's move for the next question. Read this question. Based on what we have discussed, give a try, just 1-2 minutes and try to solve it. I'm giving you the time, guys. So please, just 1 minute time le lo, try kar lo. It's a doable question, not at all difficult. You can do it. You can do it. Just switch is open at time t equal to 0. I can also just tell. Switch closed for a long time, opened at time t equal to 0. What we need to find here? Find IL of t. I hope you can do it. Now give a try. Same process. Find initial value, time constant, and you can find the response. You can observe here how I find the time constant here. I should find R equivalent from inductor side. Inductor side, what is the R equivalent? From resistor side, what is the L equivalent? Yeah. Sorry, I'll give you freshly. Try karo. Please try. Please try. Does the current source, if not mention ideal, we should assume resistor as well? No, we should not assume until unless he specify it as a practical source. By default, we should assume any current source as ideal only, right? Good. Come on, guys. Time हो गया. कोई आंसर दिया क्या? चलो, I will do it. I will only solve this question. Like previous question, here we can also give a try. So you can observe in this question, same story. Any problem, process will remain the same. Now, in this case, it is time t equal to 0. We have opened the switch. Okay. So before 0, what is the equivalent? Time t equal to 0 before. The 50-volt source is connected to the network for a long time without any disturbance. So my network is in steady state. Inductor acts as a short circuit. Okay, so this is I naught. So whenever you have short across any element, you can neglect this element, neglect this element. Now 8 parallel with 8, how much it is? 4. 4 plus 6, 10. So this will be 50 by 10, 5 ampere. By current division, this will be 2.5 and this will be 2.5. It is not because 8 and 8, because these are shorted. 0 parallel with anything. This entire can be neglected to short circuit. Total distance here is 8, total distance. We should not see immediate, total should be taken. Okay, fine. Now my I naught is equal to 2.5. Now for t greater than equal to 0, once you remove this switch, once you remove that switch, it is the equivalent. How much? 8. This will also be 8. And here you have 32, 32, and inductor with, what is the inductor initial current? 2.5. So R equivalent will be, from this side, you always see R equivalent from inductor point of view. 32 parallel with 32 parallel with 16. 32 parallel with 32 parallel with 16. For any parallel calculation, one shortcut I can give you is, if you make 32 by 1, this one is 32 by 1. Here 16 you write 32 by 2. When numerator is equal, add the denominators. Easiest way. Okay. And L equivalent is how much? 2. Tau is equal to L equivalent by R equivalent. 1 by 4. Normally formula is 1 by R equal to 1 by R1 plus 1 by R2 plus 1 by R3. It is a very simple formula here. Then what is your IL of t? I naught e power minus t by tau. That's it. Okay, 2.4 into e power minus 2.5 e power minus 4. Okay, guys. Chalo, let's move for the next. So guys, just a small announcement. We are starting our 2027 batches from February 23rd, and the fee will be very low as 6,000 per 1 year. And you have some discount. You can use this code ASK 2035. Similarly, 28 batches also we are offering you that at a price of just 11,000 using this code ASK 35. You can download the GFG app and you can try. Now, source free RC circuits. Already we have discussed this. Now, this question is to find the time constant. Okay. What is the time constant? Sir, R equivalent into C equivalent. What is the C equivalent here? 2 farad. Then what is R equivalent? So, can anybody here try for R equivalent? R equivalent means whenever you have only resistor or independent source, we replace independent source with a short circuit, voltage source with short, current source with a open, that is fine. But here you have a dependent source. How to deal with dependent source? Let us have an understanding how to deal with a dependent source. So now I need to find the R equivalent here. Just let me show you that. What is R equivalent? V by ratio. That's it. Okay. So I can find V by different ways, node analysis and all. I'll give you one easiest shortcut to solve it here. One method to find it is always when you find R equivalent, connect the source and calculate. Otherwise, you may think current in this resistor is 0 and analysis will be wrong. The same current is here Vx by 20, same current you assume, wrong. So if you take the loop equation here, I am giving you a shortcut, carefully observe. This is 4Vx and this is Vx. Then what is this one? 3Vx, right? By loop equation. 3Vx. Then what is this current? 3Vx by 10. So what is this current? 3Vx by 10. Now I assume this dependent source as a resistor whose resistance is equal to voltage by current ratio. So this is my own method to find the resistance of the dependent source. Its voltage is how much? 4Vx. Current is how much? 3Vx by 10. Arrow direction negative. So that will give you minus 40 by 3. Okay. So what is my R equivalent? Is 10 plus 20 parallel with 10 minus 40 by 3. 10 plus 20 minus 10 by 3. 30 minus 40 is minus 10 by 3. As I told you the shortcut, 20 by 1. You can write this as 20 by minus 6. 10 by minus 3. Instead of calculating, I told if you make numerator equal, add the denominators. So 10 plus 20 by 1 minus 6 is how much? Minus 5. That will give you 6. So my R equivalent is 6. C equivalent is 2. Tau is equal to 12. Okay. Tau is equal to 12 seconds. Okay. That's it. Let's move further. I hope it is clear. Chalo, let's move for the next question. I mean, the next part of the analysis. So I have some questions to solve. So let us do them. Let's give a try. So the next model of the questions is examiner can ask you initial value, final value. Anyway, you know how to find initial final value. Another model is if after switching action, network contains sources independent source. So till now in the questions we have removed the source at switching action. For example, after switching action, if independent source is present in the network, if after switching action network contains independent source, then response can be obtained by total response is equal to final value plus initial value minus final value into e power minus t by 2. Okay. So what is this here? For example, you take RL circuit. What is the formula for IL of t is given by IL of infinity plus IL of 0 minus IL of infinity into e power minus t by 2. Similarly, if you take a RC circuit, Vc of t equal to Vc of infinity plus Vc of 0 minus Vc of infinity into e power minus t by. Here you can have special cases. What are the special cases? Suppose if the final value is 0, here suppose initial value is 0, then what is the IL of t? If you substitute this 0, IL of infinity can be taken common. 1 minus e power minus t by tau. If IL of infinity equal to 0, that is nothing but final value will be 0 for source free circuits originally, right? So if you substitute final value 0, what is IL of t you will get? IL of 0 into e power minus t by tau. If the final value is 0, IL of 0 into e power minus t by tau. That is nothing but what you got in the I naught e power minus t by 2, same, right? So I can say here the formula will remain same. ये formula जो हमने discuss किया ना, it is applicable for source free or with source. In any case you can apply it. अगर initial value 0, final value 0, कोई भी case में हमने apply कर सकते. You can apply this in any condition, whether the initial value is 0, final value is 0. In every case we can happily apply this condition. So let's move further. Okay. See, there is a switch is, what is that? That is what we discussed now here. If see here, switch is closed at 0, opened before 0. This is the condition. Initial value is 0. In that case, you get IL of t is final into 1 minus e power minus t by tau. Is it clear, Vivek? So that is the condition I have explained here. So first case is source free. Second, now source is applied at 0. Before 0, no source. Source is applied at 0. This is the formula. So this is the total formula. For any case, you can apply it. Let's move further. Now, based on what we have discussed, two more conditions which are very important exam point of view is sometimes examiner asks you what is voltage across the inductor? L dAl by dt. Then what is it? dAl by dt? VL by L. Sometimes examiner will ask you find dAl by dt at time t equal to 0 plus. You can identify VL of 0 plus upon L. Similarly, he will ask you current in the capacitor IC of t equal to C dVc by dt. Then what is dVc by dt? IC of t by t. Then what is dVc by dt? Sometimes examiner will ask you what find d by dt at time t equal to 0 plus. It will be current in the capacitor at 0 plus by C. So using this, if possible, can you give a try for this question? Give a try. You need not answer it. Anyway, I will solve it and help you. Examiner has given these three informations. Final value is given, initial value is given, d by dt is given. From the given information, can we able to find the value of the resistance R? Can we be able to find the value of the resistance R? I want you people give a try and tell me the answer. Okay, come on. Come on, guys. Just use whatever I have discussed. It is sufficient to solve this. here, what is the formula he has given? IL of t equal to, okay, IL of t equal to final value examiner has given 4 plus initial value minus 8 minus final value into e power minus t by tau. What is tau? If switch is moved from position A to B, tau is equal to L by R, where L is equal to 2 here. R I don't know. We need to find that R. This is your equation. So 4 minus 12 e power minus t by tau. Okay. Now examiner has given di by dt at time t equal to 0. So what is di by dt? d by dt of constant 0 minus into minus plus 12 e power minus t by tau by tau. At what time he is saying? T equal to 0. Is it clear? Now you tell me here, if you substitute t equal to 0, what do you get? T equal to 0, 12 by tau. 12 by tau is equal to, examiner has given how much? 3. So from the given information, tau is 12 by 3. 4. Okay. But what is tau? 2 by r. R is equal to 4 by 2. 0.5 ohms. 0.5 ohms. Very simple. Just that one formula can help you many times. So using that same question, same formula, can you give a try for this question? ये फॉर्मूला यूज करो, प्रीवियसली जो फॉर्मूला हमने डिस्कस किया यूज करके इसका आंसर बता दीजिए. सो फाइनल वैल्यू इनिशियल वैल्यू यूज करके सॉल्व करके बता दीजिए. गिव ए ट्राई. सो हियर यू कैन सी, देखो, you can see here in the circuit shown in the figure, the switch is open for a long time and closed at time t equal to 0. So firstly, what is the initial value means? Before the switching action, what is the value you need to identify? So before time t equal to 0, okay, long time, whenever he say network is in which state? Steady state. 20 volts, this is 10 and 10. Okay, switch is like this and capacitor acts as an open circuit. Because before 0, network is in steady state. Capacitor opens. Okay. Now, at time t equal to infinity, again, network is in steady state. Okay, if you close the switch, this is 20, 10, 10, capacitor acts as an open. Now you see here, capacitor is open circuited. What is this voltage? This is Vc of infinity. Just apply node equation here. V minus 20 by 10, V by 10, V minus 10 by 2 equal to 0. So here you get V minus 20 plus V. I can take LCM, right? 5V minus 50 equal to 0. So from this again you get V equal to 10 only, because 7V equal to 70, V equal to 10. So what is the initial value you got? Same. Final value same. Whenever initial value and final value are same, there will not be any transient in the network. Whenever initial value and final value are same, there will not be any transient. So what is your VC of t equal to? Final value plus initial minus final e power minus t by tau. That is constant for t greater than equal to 0. So here what happens when you close the switch, already it is 10 volt, it will stay at 10 volt only. So no current will be flowing here. If you want, you can find this current by node analysis, or you can find IC. From that IC you can find the current. Okay, but what is the current you will get is 0. Because this node voltage will be at how much? At 10. Okay. Uh, then how much current you will get at 10 by this node? After closing the switch, this will be 10. This will also be 10 because it is shorted. 10 by 10, 1 ampere. If it is 10 and if it is 10, 10 minus 10 is 0 current. Okay. And this is 20 minus 10, 10 by 10, 1 ampere. 1 comes and 1 leaves. And this current is 0. This current is 0. By KCL, this will also be 0. So this is a very trivial case where final value and initial value are equal. Then there will not be any transient in the system. It is also a same model. So let's do some interesting question here. Whatever we have applied, whatever we have discussed, that final value plus initial minus final e power minus t by tau, using that only, let's give a try to solve this question. So let me first explain the meaning of the question. In the microprocessor controlled, whenever you see this microprocessor and all, you may feel, yaar, this is not my part, it is very difficult. Aisa kuch nahi, just have a patience to read the question, understand or use the informations which is required for us. Okay. So measured scheme shown in the figure. Rx is the unknown resistance. Yeah, Rx जो है ना वो unknown resistance है. We don't know the value of the Rx to be measured. While R reference and C reference is known. Okay, are known. C reference is charged. C reference is the capacitor which is getting charged from VL to VH. VL to VH by a constant DC source of Vs. Okay, this analog interface will be having some Vs that will be charging this RC circuit. Okay, once through R reference, use it in a time of T reference. Okay, then discharged again to VL. VL inductor voltage is at VL. It is charged to VH. How much time it required? T reference time. Using which one? R reference. Using R reference, in T reference times, it charged from VL to VH. Then it is discharged to VL. Now it is again charged from VL to VH. Through which resistance? Rx. Through Rx in Tx seconds. Then what microprocessor is doing here? It is controlling that part. We should assume like that. Okay. So what is this sense charge discharge? Means whenever it reaches VH, it will discharge to VL. That is done by this part. Okay. It is again charged in Tx seconds. So if Tx equal to K times T reference, then he is asking Rx value. He is asking Rx value. We will see what is the value of Rx. Rx is the unknown resistance. We need to find it using the information given. If possible, you can give a try. I can give you 1-2 minutes of time. It's a very good question. Forget about options. Yeah. Please try. Come on, guys. Please give a try. It's a good question. 30 seconds more. $20. Any answer? Come on, guys. Okay, chalo, I'll do it. Let me solve it. So just use the information given by examiner. Firstly, first what he has used, using R reference and C reference, using my R reference and C reference, capacitor is getting charged using the voltage source Vs. It is charged to VL to VH. So can you tell me here, what is the initial voltage here? Sir, initial voltage is VL. What is the final voltage? What is final voltage? Very important question here. Many people will confuse here and give you the wrong answer. So this is my VC. Capacitor is getting charged from VL to VH in how much time? T reference time. T reference time. So V naught is equal to initially VL. Now we need to find VC of infinity. We need to find VC of infinity. I mean, what is VC of infinity means? Don't take VH. VH is the voltage at time t equal to t reference. It is not the voltage at infinity. If you don't disturb this circuit, what is the voltage it will reach is Vs. Because capacitor requires how much, source is how much? Vs. He said voltage Vs is connected, right? So be careful. After that, it is a normal question. So what is the voltage across the capacitor? Formula Vc of t equal to final value plus initial value into initial value minus final value into e power minus. So don't take here final value as VH. VH is the value at t reference. Final value means we should take infinite time. If you don't disturb it up to infinity, what is the voltage you will be getting? That is the final value. So t by tau. Tau is how much? Tau is equal to how much? Tau is equal to, it is T reference. Tau is equal to R reference into C reference. Okay. Now examiner is saying that at time t equal to T reference, my VC will be equal to VH. Okay. VC will be equal to V reference. Okay. We'll use it later. Next, again same way, VC will be equal to VH. It is reaching VH and substituted time t equal to T reference. Same way, second possibility is, now he has connected RX, same capacitor C reference, and voltage Vs is the source. Now it is connected from charging, discharged to VL and charging from VL to VH. In how much time? Tx. Okay. So now what is your VC of t? VC of t equal to same final value plus initial minus final, because it is said it is discharged to VL and charged, e power minus t by tau. So that is Vs plus VL minus Vs into e power minus t by tau is how much here now? Tau is equal to Rx into C reference. Rx into C reference. Now what is your tau x? Rx into C reference. Okay. Now you can observe carefully. Observe carefully. At time t equal to Tx, capacitor voltage becomes Vh. Vh equal to Vs, Vl minus Vs, e power minus t by Rx into C reference. Now, suppose you take this as equation 1, equation 2, equate 1 comma 2. Why sir? Because both are VH, here also VH, here also VH. Then VS cancels, VL minus S, VL minus VLS cancels. So, what do you get here? Minus minus, or you can say T reference by tau is how much? R reference into C reference, CXR. C reference is equal to tau Tx by Rx into C reference. So C reference cancels. What is your Rx is R reference into Tx by T reference. Now you see, what is the Tx by T reference? K. Substitute that, you get Rx equal to K times R reference. So what is the answer? Rx equal to K times R reference. You observe here very simple question. My capacitor is charged from VL to VH at time t equal to T reference. Here at time t equal to Tx. In this case, tau is R reference into C reference. Here tau is Rx into C reference. Equate this with this because both are VH. Vs cancels. VL minus S, VL minus Vs cancels. E cancels. Then this part will be equal to this part. From that, I find the relation for Rx with respect to R reference. Chalo, let's move further. See this question. If Vc of 0 equal to 6 volts, initial voltage across the capacitor is 6 volts, determine the energy delivered by the source from time t equal to 0 to infinity. Suppose this is a DC source connected to the RC circuit. Okay, its initial voltage is given as 6. Nothing is specified. We may take it as 0 also. Now, what is the energy delivered by this source from time t equal to 0 to infinity? Okay, what is the energy formula of CV square? But here energy is not capacitor energy. Energy delivered by source he asked. Okay, right? So I'll do it. In this case, what is the answer here? Firstly, what is Vc of infinity in this case? If you don't disturb this network up to infinity, capacitor acts as an open circuit, you will get 10. Vc of 0 is how much? 6. Then what is the formula for Vc of t? And also tau, R equivalent into C equivalent, 8. What is Vc of t here? Final value plus initial minus final e power minus t by tau. 10 minus 4 e power minus t by tau. Okay, that is my Vc of t. Wait. Now, what is the current in the capacitor ICO? C dVc by dt. C is 2, d by dt of constant, 0, minus into minus plus, 4 by 8. So this will be e power minus t. Why I am doing this, I'll tell you. Because examiner asked energy. Energy is taken by resistor, energy taken by capacitor. We need to find both of them because energy delivered by source he asked, not EC. He asked ER plus EC. Okay, I find IC and VC, just direct formulas. Now, because the network is same, series IR equal to IC. Then what is the energy taken by the resistor? Integration of 0 to infinity I square. I square is how much? E power minus t by 8 whole square into R. R is how much? 4 dt. So calculate this part, you get 16 joules. I'm not doing this basic integration. You get e power minus t by 4 by minus 1 by 4. You'll get all that stuff you can do. Now, energy in the capacitor. What is EC of infinity? Of C VC of infinite square. So half into C is how much? 2 into Vc of infinity how much? 10 square. 100 joules. But in this question, examiner has given initial voltage which is not given by the battery. How much it is? 6. That is half C is how much? 2, 6 square, 36 joules. So what is the energy in the capacitor from 0 to infinity means? You should take a final value 100 minus initial value 64 joules. So total energy equal to ER plus EC. What is your ER? 16, EC 64, 80 joules. That is the total energy supplied by the source from 0 to infinity. Here 2 points, we should consider the energy of the resistor. We also should consider the initial value which is already present to be subtracted. Very, 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 very important. You can also see, instead of doing this much stuff, you can also use the formula integration of voltage into current. Voltage is how much? 10. Current is how much? E power minus t by 8 dt. You can try in this way also, you get the same answer. Here, very, very important logic I want to give you is, in this question, if Vc of 0 equal to 0, energy taken from 0 to infinity is equal to energy taken from 0 to infinity for both resistor and capacitor are equal. So what is the energy E from 0 to infinity? It is ER plus EC, that will be 2 times EC, which is 2 into half C VC of infinity square, because initial value is not present. That will give you CVC of it. So this formula is very useful. If suppose examiner give you the question with initially unenergized, then you can use the formula CVC of infinity square. So kindly apply that in this question. Tell me the answer. What is the answer? In a RC circuit with initial voltage 0, the ratio of energy taken by resistor to energy supplied by the source. Energy supplied contains resistor and capacitor. What is the ratio of energy taken by resistor to energy supplied? What is the ratio? What is the ratio? 50%. 50%. So try this question, because ER equal to EC, ER upon ER plus EC. So try this question based on what we have discussed. I hope you can do it. It's a very easy question. Based on what we have discussed, you can definitely able to solve it. Please give a try. Please give a try. Come on, guys. It's doable. Okay, I'll do it. Direct answer you can give. Okay. Okay. Chalo. Listen. Very simple question. Here also same. Initially no capacitor energy. So what is the formula? EC of E of infinity equal to 2 times C into VC of infinity. 29. This is what we have discussed. Okay. So C is how much? 0.1 into VC of infinity is 0.9 microjoules. That's it. Because it is microfarads. Because VC of 0 equal to 0. One step you will get the answer. Same model, try at least this question. Try at least this one. Here also initially no energy. VC of 0 equal to 0. I hope you can answer this question. Just the same application. VC of infinity is 10. If you replace capacitor with open circuit, then what is EC of infinity? What is EC from 0 to infinity? Or what is E? Energy, total energy from 0 to infinity. Same formula, C into VC of infinity. So 1 into 10 square, 100 joules. That's it. Okay. So let's move for one more question. So give a try. This is a beautiful question. The instantaneous charging of capacitor comes into picture here. You can give a try for this question. So please give a try. It's a very good question. I have a 1 farad capacitor with initial voltage of minus 1 volt. So see here. What is VC of 0? Minus 1 volt. I connected this to a ideal voltage source of 1 volt. Then what is VC of infinity? Very interesting question here. So what is the energy in the capacitor at 0? Half C V square 1 by 2 joules. What is the energy in the capacitor at infinity? Half C minus 1 or 1 doesn't matter, right? 1. So what is the energy in the capacitor gained? EC of infinity minus EC of 0? 0. So how much, there is no other element in the network. How much energy is given by the battery is the question. How much energy is given by the battery is the question. So how much energy is given by the battery? Can I take 0 as the answer? Means no. Here you don't apply law of conservation of energy. It doesn't mean that it will fail, but there is a violation of KVL in this circuit. There, violation of KVL is nothing but law of conservation of energy. In that case, we should not apply law of conservation of energy directly. It is applicable, but there is some indirect or some point we need to understand that I will show you. So in this case, always try to solve by Laplace. So generally, basic common sense, my voltage is at minus 1. I'm charging it. I want to bring it from -1 to +1. To bring the capacitor voltage from -1 to +1, I need to do some work or not? I means the voltage source. It need to do some work. To do that work, definitely it requires some energy. कोई काम करने के लिए हमको एनर्जी चाहिए ना, सेम वे आपका वोल्टेज सोर्स को भी एनर्जी इज रिक्वायर्ड टू मूव द वोल्टेज फ्रॉम -1 टू +1. इसलिए कंपलसरी एनर्जी तो जीरो नहीं हो पाएगा. सो इस वाला केसेस में हमने क्या करना, लैपलेस से सॉल्व करके चेक करना. हाउ कैन आई सॉल्व बाय लैपलेस? व्हाई? बिकॉज सी आई एम अप्लाइंग 1 volt here to the circuit at time t equal to 0 plus. Capacitor is already having initial voltage of -1. So at time t equal to 0 plus, when you close this switch, capacitor is already having some initial voltage -1. Capacitor acts as a short circuit. So this process +1 and -1 are in parallel will give you violation of KVL. Whenever violation of KVL happens, solve by Laplace. I will show you. This input is 1 by S. What is the Laplace equivalent of the capacitor, which we discussed earlier? V naught by S, which is -1 by S, series with 1 by SC ohms. Current will be I of S. 1 by S minus of minus plus 1 by S by 1 by S, which will give you 2. Constant. What is the inverse Laplace transform? 2 del of. So then what is your VC of t? VC of t equal to, current is given, okay. Just so for impulse, what happens? For impulse, capacitor can charge instantaneously. This is the condition of instantaneous charging of the capacitor because there is no resistance. Okay. What is the energy formula? Integration of 0 to infinity. Voltage V into current I dt. So integration of 0 to infinity. Voltage is how much? 1 volt. Current is how much? 2 del of t. Del of t integration is 1. So 2 joules. This is the answer. So when you are lifting capacitor from -1 to +1, how much the total energy required is equal to? Here you can also say the formula will be C into V2 minus V1, final minus initial whole square. But you can do by Laplace and you can visualize the impulse. This is instantaneous charging of the capacitor. Now you may get the doubt, sir. Okay, all are correct. It is energy 2 joules, or it requires 2 joules of energy to spend to charge it from -1 to +1. But initial energy in the capacitor and final energy in the capacitor is 0. If these 2 joules are spent, where this 2 joules is gone? If you have a resistor, we can say it is dissipated in the form of heat. Here there is no resistor, no element is present. Then how energy will be wasted? In this is a very trivial case. Current, what is that? Current voltage is equal to I into R. Energy equal to integration of I square into R. If R is 0, no energy should be taken by the resistor. But here I is non-zero. I is infinity. I is not a regular value. I is infinity. So infinite into 0, can you define it? Naina? So here is case mein kya hota hai na? The moment you close the switch, due to violation of KVL, spark will be generated. That spark will be, energy will be escaped in the form of spark. Okay. So here infinite current will flow through the 0 ohm resistor. So if resistor is a finite value, then if resistor is 0, if current is finite value, it will not, what we call energy will not be dissipated. But here current is infinite value. So that is about this particular question. So this is also one important model. Two capacitors with different initial voltages are connected in a loop. Here I will give you direct formula for final value of the capacitor equal to final value of the second capacitor, because one will be discharging, one will be charging. At one constant, both are equal. This is equal to C1 V1 plus C2 V2 by C1 C. So C1 is how much? 1. V1 is 2. C2 V2 by C1 plus C2. get 5/3. Okay, this is the what we call the final value when capacitors are connected in a loop. We can solve by Laplace and prove it also. Now please try to answer this question if possible. Answer this question. Please give a try. Come on guys, you can do this. So let me finish transient, then I will give you break 10 मिनट का. इसके बाद हमने AC analysis last chapter शुरू करेगा. So here what happens is capacitor with 12 volts with short circuit. No initial, because time t equal to 0 plus capacitor acts as a short circuit. Once you close the switch, what happens? When two capacitors of different voltages are connected, here violation of KVL, like previous case, this case may be impulse generate होगा है. Impulse generate होगा है. Okay. Now, based on that particular model, we can also solve this question. Here, what he has given, the initial voltage across the capacitor C1 is 1 volt, C2 is 3 volt. What is the total energy dissipated in the resistor? Very simple. First find using our formula I have given. मैंने जो formula दिया ना इसको use करके final value निकाल लो. What is the final value? V1 of infinity equal to V2 of infinity equal to, what is the formula? C1 V1 plus C2 V2 by C1 plus C2. So मैंने C1 कितना दिया? 3, C2 V2 by C1 plus C2. So 6 by 4, 1.5. Up to this clear, right? Now 1.5 joules mila. Then 1.5 volts. Now what is the initial energy? Initial energy stored in the capacitor. Half C1 V1 square plus half C2 V2 square. So half into C1 is how much? 3. V1 is how much? 1 square. Half into C2 is how much? 1. V2 3 square. That will give you 1 by 2, 9 by 2, 10 by 2. I don't think right. 1 minute. C1 into V1 square. C1 V1 square half C2 into V2 square. 9 by 2 is 4.5. 3 by 2 is 1.5. So 6 joules. Okay. What is the final stored energy? Of C1 V1 square. 1.5 is 3 by 2 whole square plus half C2 V2 square is again 3 by 2 whole square. So that will give you 9 by 4 plus 3 by 4 by 4. This one is how much? 9 by 4, right? 9 by 4 plus 3 by 2 plus 1 by 2 is 2. 9 by 2, 4.5 joules. So what I want to say here is, ये कैपेसिटर के पास कितना वोल्टेज है इनिशियली? 3 volt. Sorry, 1 volt. It is having 3 volts. What happens? Once you close the switch, this will be discharging, this will be charging. Once this is discharging, it is charging, current will flow. During that current flow, this resistor will eat the energy. When current is flowing through the resistor, it will dissipate the energy in the form of heat I square into RT, right? Or integration of I square into R dt. So when this is discharging, this is charging, capacitor will be, so this resistor will be enjoying or dissipating some energy. Once they both of them are equal, current will become zero. There will not be any charging or discharging. So initially 6 both of them will be having. Finally 4.5 they are having. So the remaining 1.5, that is 6 minus 1.5 is the energy taken by the resistor from 0 to infinity. So we can also do this by finding current in the resistor, and that will take a lot of time. I square into R integration, it will take a lot of time. So this is the best method. Chalo, next. For your practice, you can try the same model. Capacitor charge is asked Q equal to CV. Similarly, we can also solve the second order systems. Whenever second order system means RLC circuit, we should solve by Laplace. For example, here VC is asked. What is del of t? 1 S 1 by S. Then what is VC of S? 1 into 1 by S by S plus 1 plus 1 by S. Take the Laplace transform, 1 upon S square plus 1 plus S square plus S plus 1. So you can try this by mathematically, I can write it as 1 by S square plus 2 times 1 by 2 into S plus 1 by 2 whole square plus root 3 by 2 whole square. Why I am doing like this, I will tell you. A square plus B square plus 2AB. 1 is written as 1 by 4 plus 3 by 4. So I can write this as 1 by S plus 1 by 2 whole square plus root 3 by 2 whole square. Okay, because what is the inverse Laplace transform of B by S plus A whole square plus B square e power minus AT sine BT u of t. I am just trying to convert this in that format. Okay, then multiply with 2 by root 3 into root 3 by 2. So it will give you 2 by root 3. That is my current in the time domain into B by this formula. If you use e power minus 1 by 2t sine root u of t for t greater than equal to 0. This one. Okay. So like that, second order systems we always solve by Laplace. If numerator is containing S term, it is cos term. Constant, it will be sine term. Like that we can solve. So that is about your transients. There are some questions like just give me one. Damping conditions. Anyway, you study in control systems also. I'm not reading that part. Underdamped, undamped response, etc. Zeta. This is a. We can also have LC circuit. For analyzing LC or RLC, in any case, second order system means take Laplace transform. Okay. So there are some special cases. Sometimes operated 2 times. In that case also we can find the response. Sometimes examiner will give you current is in the series circuit. Current in the series circuit is given, directly we can find the response. Okay, current is given in the series circuit, we can directly find the response by KCL and KVL. Voltage is given in the parallel circuit, then also we can directly find it. Okay, and whenever current in the capacitor is constant, you will get a ramp generation. Similarly, voltage across the inductor is constant, then also you will get the ramp generation. All these are special case of problems. I have added them in the notes. You can refer them. So here sometimes examiner will give you multiple switches in the network. When they give multiple switches, first you find the response for one switch closed and find the response. For example, here first switch is closed, right? So this is the circuit, capacitor with initial voltage. So what is your VC? 12 e power minus t by tau is how much? R into C. This is for t greater than equal to 0, less than or equal to 3. So what is VC of 3 here? 12 into e power minus 3 by 3, 4.4 something will get. Now after 3, this switch is closed, for example. Now the circuit will be like this. 1. Now the capacitor will have new initial voltage. What is the initial voltage? 4.4 series with 1. Now what is VC of t is, we should take 4.4 e power minus, please listen carefully, t by tau. Tau is how much here? R into C, 1. But here instead of t, you should write t minus 3. Okay. T by tau का जगह पे t minus t naught into, this is t minus t naught when second switch is operated at time t equal to 3. Okay. This is up to 3, after 3, second switch. So t greater than 0, normally we will write t here, t minus 3, you should take it. Okay. So this is how you will be solving these kind of questions. Sometimes examiner will give you pulse as excitation. There also see here. Pulse is given. How do you find? Up to this point, you assume network is with source. After this point, network is source free for t greater than 2. So it is like a 2 switches. One switch is applied at 3 volts. Another switch is removed at 2 seconds. Assume it is a DC source only. Find the total response. Find response by assuming DC. Find VC of t. Okay, you will get some V naught e power minus t by tau or 1 minus e power minus t by tau into VC of infinity. Okay, then find VC of 2 minus, which is equal to something, VC of 2 plus. For t greater than equal to 2, what is VC of t equal to? Your VC of 2 minus into e power minus t का जगह पे t minus 2 by. Got it? So source free circuit. That is how we will be finding the pulse excitation. So let's take a break for 10 minutes. After that, I will start the session of AC analysis. We'll discuss the AC analysis part of it. Just one moment. We'll take a break, just 10 minutes. We'll be back. I'll be back. Okay. I'll be back in 10 minutes. Okay, welcome back. Oh. So now let's start the next part, AC analysis. So last chapter of our discussion, AC analysis. So here, firstly, the very basic of the AC circuits is phasor representation. Suppose I have a signal. V of t equal to, say, Vm cos omega t plus phi. I can write this as root 2 into Vrms cos omega t plus phi, or root 2 into Vrms cos theta can be written as a real part of e power j omega t plus phi, e power j omega t into j. So root 2 into the real part of v into e power j omega t. What is v here is the phasor Vrms e power j phi, or Vrms angle phi, Vrms e power j phi can be written as cos phi plus j sin phi. All are valid. All are valid. Okay. So now see here. Okay. Uh, Sometimes instead of RMS, we will also take maximum value and represent it. There are different ways for phasor representation. Even sin theta can also be represented directly, or you can also write cos omega t minus 90 degrees is equal to sin omega. We can use this relation, or you can directly take the sign. All are possibly valid correct answers, but by default standard is cos. Okay. So one of the exam they have given this question. The voltage applied to the circuit is 100 root 2 cos this one, and current is this one, taking voltage as the reference. So cos is your reference. The phasor for current is. So what is that? 10 root 2 sine 1000 t plus pi by 4. So first convert into cosinusoidal. 1900. Okay. So take here convert into sine into cos. So that will give you 10 root 2 cos 100 pi t minus pi by 4. Okay. So now this is your I of t. What is the I equal to IRMS, that is 10 angle minus pi by 4. You can see here 10 root 2 is also there minus pi by 4, but that is also originally correct according to some textbooks. Nothing specified, by default choose RMS value. So in transient also we have DC transient and AC transient. In series RL circuit, if sinusoidal excitation, if the initial phase of excitation is tan inverse omega L by R, then there will not be any transient in the RL circuit. Similarly, for this one RC circuit, if it is cos at the time of I'm not going much in this part because they are not, they don't ask this very frequently. Because of the 90 degrees phase shift, this is the condition for transient free. So this is the circuit. So I have a RL circuit. For AC condition, what happens? What is the condition for transient free? If initial value, final value same, no transient. So if you close the switch at one time such that this condition is satisfied in RL circuit, there will not be any transient for AC case. Similarly, for RC, the transient precondition for RL RC, for RC, what is the transient precondition is omega t plus phi at the time of closing switch equal to tan inverse omega RC. So in RL and RC circuit, transient preconditions are dependent on initial phase, frequency, RL constant, but it will never depend on the magnitude of the excitation. I'm little quickly going through this because for RLC there is no transient precondition. What is the meaning of transient free? No transients at the time of switching. This is one question. I'm not transient free के लिए. So let's solve this question based on both of them. It is a combination of AC circuits and DC transients. So it is given in electrical engineering question paper GATE 2024. Okay, so let's give a try. Chalo. So this is a very interesting question. So please pay attention. The circuit shown in the figure is initially steady state. Okay. With the switch K is open, this switch is open and K bar is closed. With this K open and K bar closed condition. With K open, K bar is closed condition. What happens? The switch is 1 minute. It is the circuit shown in the figure. Initially, the steady state with K is open and K bar is closed. The switch K is closed and K bar is opened at a time t equal to t1. So initially, what happens? Initially, K is open and K bar is closed. Okay. At time t equal to t1 उल्टा किया. उल्टा का मतलब क्या? K bar को open करके K को close किया. Where t1 is greater than 0, t1 is a positive quantity. The minimum value of t1 such that no transient in voltage across the 100 microfarad capacitor. Firstly, let us analyze this circuit before t1. For t less than t1. Network is in the steady state. This is 10 ohm. So I have a current source of 1 angle 0 degrees. I'm writing in the phasor domain. Okay. With this switch is open, this switch closed means isko neglect karo. Then capacitor will be replaced with what is 1 by j omega c here? 1 by j 1000 into 10 power minus 4. So minus j10. Now examiner, I want to find this VC. This is my IC. Okay. So what is current in the capacitor? 1 into total current into opposite resistance by total resistance. What is VC? This impedance minus j10 into 10 by 10 minus j10. Okay. So what I'm writing here, VC equal to, what is that? Minus j10 into 10 upon 10 minus j10 is 10 root 2 because a square plus b square, 10 square plus 10 square will give you root 100 plus 100, root 200 is 10 root 2, tan inverse of negative angle minus theta minus 45. 10 cancels. So what do you get? Minus j into 5 root 2 angle 45 degrees. Or you can say 5 root 2 angle minus 45 degrees. So what is your VC of t is? Because you have taken sine as the reference in this case, your answer should also be considered as sine. Because you have taken here maximum value, because 1 sine 1000 t maximum, response also to be considered. Whatever you take here, same you should take it in the reverse. So 5 root 2 sine What is that? 1000 T minus 45 degrees. So this is my voltage across the capacitor before T1. At time T equal to T1, what happens? This switch is closed and this switch is open. Now you see here. So what is your VC of T? 5 root 2 sine 1000 T minus 45 degrees up to time T1. Now, for T greater than equal to T1, once you close this switch, it is shorted. This total current will flow here. So this part is not affecting your capacitor. So capacitor will be like this. Capacitor will have initial voltage V naught. Okay. Initial voltage V naught or VC of T1 in series with a capacitance. Okay. Now, so can you tell me what is VC of infinity here? If you open circuit this capacitor, VC of infinity will be 5 volts. So what is your formula for VC of T is VC of infinity plus VC of infinity minus VC of T1 in final value minus initial value e power minus T by tau. Okay, T minus T1 also you can take it, no issue. T minus, or you can take T minus T1 for proper mathematical representation. If you consider T equal to T1 here, fine, no issue. But here, if VC of infinity equal to VC of T1, then what is my VC of T equal to? If both are equal, ये 0 हो पाएगा, I'll get VC of infinity, no transient. So what is the required condition for no transient in this case? Final value should be equal to initial value. So how can I achieve that? So my VC of T1 should be 5 root 2 sine 1000 T minus 45 degrees must be equal to 5. The moment you are closing switch, capacitor is, say, the voltage will be like this, sinusoidal voltage. When its value is 5 volts, I should close the switch. That is the meaning. I should operate the switch when its value is 5 volts, then final value and initial value same. Okay, there will not be any transient in the network. Okay, there will not be any transient in the network. So, sine 1000 T minus pi by 4 must be equal to 1 by root. So, 1000 T minus pi by 4 equal to sine inverse of 1 by root, which will give you pi by 4. So 1000 T equal to, take this pi by 4 other side, pi by 4 plus pi by 4 will give you pi by 2, and T1, T1, T1. So what is your T1 is equal to pi by 2 milliseconds. Pi by 2 is 3.14, will give you 1.57 milliseconds. 1.57 milliseconds. Let's move for the next. So now in the AC analysis, what are the topics we have broadly? We can say sinusoidal steady state analysis, that is when sinusoidal input is applied to a network which is in steady state, how the response will be. इसके अलावा phasor diagram, average RMS values, complex power calculations, resonance, locus diagrams, filters, magnetically coupled circuits and three phase. So इसमें ज़्यादा रिवाइज करने के लिए नहीं, so I don't discuss much about them, but ये होता है resonance is very important. Power calculations में हम concentrate करेगा. So and ये दोनों जो टॉपिक है ना, एक केवल इलेक्ट्रिकल को है, ईसी वाला बच्चों के लिए नहीं चाहिए. And electrical people, they are definitely getting one question from three-phase circuits. So this is your total AC analysis. So let us see the first part, sinusoidal steady state analysis. So steady state का मतलब क्या होता है? Steady state means absence of transients. When you achieve that absence of transients after 5 time constants after the switching action. After 5 time constant of the switching action, we achieve the steady state condition. At steady state, generally the steady state analysis in the AC circuits, how we evaluate is by using phasor approach. Let me show you how you analyze the circuit in the steady state. Suppose I have a network like this. एक resistor, दूसरा resistor, inductor और capacitor. Okay. So this is my current I1 of t and I have another current I2 of. Say for example, I need to find I1, I2, assume network in the steady state. आप steady state पे assume करके I1 I of t निकालना, I2 I1 and I2 निकालना चाहिए. कैसा करना? How can I do that? Let us see. So how I can achieve this? Very simple. First, we need to convert this network into steady state phasor domain. So I told here the phasor can be maximum or RMS, but examiner gives any phasor, consider it as a RMS. When you are solving, you can, as per your convenience, you can take VM angle phi. This is R1. Inductor in the phasor domain is J omega L. R2. Capacitor in the phasor domain 1 upon J omega. Say this is my current I1 and current I2. Based on current direction, मैंने polarities दे दिया. So what is the KVL in the first loop? VM angle phi minus I1 R1 minus I1 minus I2. Because you are in the first loop, this is your reference into J omega L equal to 0. It will give you one equation. What is the KVL in the second loop? Minus I2 R2 minus 1 upon J omega C into I2 minus I2 minus I1 into J omega L equal to 0. If you solve your first and second solutions, you will get I1 and I2. But I1 ऐसा आएगा IM1 because you take here maximum, you will get maximum angle phi 1. I2 will be coming out as some IM2 angle phi 2. So then I1 of t equal to IM1 cos omega t plus phi 1. I2 of t equal to IM2 cos omega t plus phi 2. So that's it about your I1 or I2. Okay. So that is the process or procedure to find the response of a any network with the sinusoidal excitation in the steady state. Okay, chalo. Now, one of the important tool to find the response of AC circuits is with the help of phasor diagrams. One of the important tool to find the response of the AC circuits is using phasor diagrams. So let us see how can I apply the concept of phasor diagrams to find the response in the AC circuits. Say first example I want to take series RL circuit. Series RL circuit. Okay. So whenever it is inductor in the AC case, we should replace with J omega L. So this is my current, voltage across the resistor and inductor. So how do you draw the phasor diagram for this? From the phasor diagram, how I can find the response? So my VR will be equal to I into R. My voltage across inductor is I J omega L, or I can say I XL angle 90 degrees. What is the loop equation? V equal to VR plus VL. Now let us draw the phasor diagram here. So since it is a series circuit में current constant होता है ना, so because it is a series circuit, let me take the current I. Okay, voltage across the resistor is in phase with the current. Voltage across inductor is at 90 degrees. 90 degrees means it will be like this. Now, if you add VR and VL, what is the resultant vector will be vectorial addition of these two will give me this much. Vectorial addition of VR and VL will give me this much. Okay. So what is your V? Root of vectorially VR square plus VL square. So here the phi will be tan inverse of VL upon VO. Tan inverse of opposite by adjacent. Or you can also write tan inverse of XL upon R because V equal to IR. Okay. So you can also draw this as a impedance phasor diagram R, X and J. Okay. So here one important condition called power factor, which is cos phi equal to VR by V. That is also given as R by Z. Here overall current compared to overall voltage is lagging. We call it as lagging power factor. Because cos theta is positive or negative, result will be same. So we should represent current is lagging behind the voltage or leading behind the voltage. So here voltage and current relationship is obtained. The angle between source voltage and source current is given by phi. So similarly, if you take a RC circuit also, we can plot the phasor diagram. For RC circuit, you just get in the reverse. You just get in the reverse, it will be leading. You have RLC circuit also, you can plot the phasor diagram. For RLC circuit, what happens? It depends on, I will show you. Suppose the same circuit I asked for RLC, then I will have RLC में क्या होता है? This is my I, this is my VR, this will be VL, and this will be VC. So result will be VL minus VC if VL is more, or VC minus VL if VC is more. Then add them. Okay, I'll show you this. Similarly, we can plot for RC. RC, you get leading power factor. Current will be what we call leading the voltage. So for RLC, what happens? RLC. Now, what is VR? What is VL? IJXL. What is VC? Minus IJX. Okay. So here, if you plot, because series circuit, I will take current as the reference. Okay. This will be VR. VR current voltage across resistor is I into R. It is always in phase with the current. What about voltage across the inductor? It is at plus 90 degrees. Voltage across the inductor is plus 90 degrees. Okay. What about voltage across capacitor? Minus 90 degrees. Okay. So which one? For example, so here three possibilities are there. VL is more, VC is more, both are equal. So first I am taking first possibility. Say XL is greater than XC. That is magnitude of VL greater than magnitude of VC. Similarly, we can have XC greater than XL and XL is equal to XC. Here you get unity power factor. Here you get leading power factor. Here what happens? VL is more than VC. Result will be VL because two vectors with 180 degrees phase shift, resultant will be subtraction. So here what happens? This will be okay. So what is your V here? Root of VR square plus VL minus VC whole square. And what is your phi? Tan inverse of VL minus VC by VR. And power factor cos phi equal to VR by V. But current you observe lagging behind the voltage. If the same question is asked for XC more than XL, leading, both are equal, VL, VC will cancel and VR will be equal to V and power factor will be equal to 1. Power factor is equal to 1. Power factor is equal to 1. Okay, let's move. So parallel RL circuit, the current is I, resistance is R, inductor we can replace with JXL. Okay, so this will be V, parallel voltage is same. Current will be IR and IL. Okay, what is your IR? V by R. IL V upon J XL, that is V upon XL angle minus 90 degrees. By KCL, total current I will be equal to IR plus IA. Okay. So this is the parallel RL circuit. Now take parallel voltage is same. So you should take voltage as the reference. Okay. How do you draw the phasor diagram? I'm explaining. Current in the resistor is in phase. Current in the resistor is same. What about current in the inductor? Minus 90 degrees. So current in the inductor will be minus 90 degrees. Okay. Now if you add them, I'll get the total current. So what is the total current I? Root of IR square plus IL square. Okay. Phi tan inverse of IL upon IR. This will give you Z by R. There R by Z, here Z by R, because this will be V by R and V by Z, right? It is actually G, V and Y. Admittance triangle we also call it. Okay. Power factor is equal to G by Y also. Okay. But here current is lagging. RL circuit always current will be lagging. RC circuit current always leading. When both are equal, you will get unity power factor like a resistive circuit. So this is about phasor diagrams of RL, RC, RLC circuits under various conditions. So based on what we discussed just now, try to answer these questions. Please give a try to answer this question. इसमें पैरेलल आरएल सर्किट दिया, इसमें करंट इन द रेजिस्टर दिया, करंट इन द इंडक्टर. यूजिंग बोथ ऑफ देम यू नीड टू फाइंड द टोटल करंट. So give a try and find the solution for this. Okay. Now the current in the resistor is given by 6. Current in the inductor 8. Total current will be root of IR square plus IL square. Okay. 10 amperes. So this is from the phasor diagram analysis. So similarly, determine the angle between VL and VS. Please try this. Please try. Okay, चलो इस केस में क्या होता है ना, you need to find the, here you can follow the question by phasor diagram. Another case is both of the elements are in series. So what is the voltage across the inductor is total voltage into I can write 17.3 as a 10 root 3 total voltage into this particular inductance J10 by 10 root 3 plus J10. So Vs into 10 angle 90 degrees by root of a square plus b square will give you 20 angle. Tan inverse b by a 1 by root 3 will give you 30 degrees. So this will be Vs by 2 angle 60 degrees. So this phi will be how much? 60 degrees. This is one method. Otherwise, we can also use the formula uh, tan inverse of let's take phi. Phi equal to tan inverse of omega L by R. Tan inverse omega L is how much? 10. R is how much? 10 root 3. That is give you 30 degrees. So, for example, but here 30 RI, here 60 RI. Why there is a contradiction? Please understand that the angle 30 degrees is not angle between VL and VS. It is voltage and current. So, this is your current. Okay, this is your VR, VL and V. So, this is my phi. Okay, so this phi, this phi is 30 degrees. Already we know this is 90 degrees. But examiner question is not angle between V and I. It is angle between VL and VS. So in this way also VL and VS 30 plus 90, 120, 180 minus 120 is 60 degrees. Okay. So any method you can solve directly like this also. But what he asked is angle between VL and VS. We should be careful. We must be careful about that. Let's move. Same model, one more question. 240 cos omega t is the input, XL is given, XC is given. Using these three informations, we need to find the average power dissipated, and also the power factor. If you are able to try, you can give a try. Otherwise, anyway, I will solve it. Just 1 minute, I can wait for you if you can able to solve it from the given information. Okay, come on. Okay, chalo. So here the input is 240. Whenever you are calculating power, always consider RMS value 240 by root 2. Why this is happening? So this will be 240 upon root 2. Otherwise, take 240 only. What is the problem? While calculating power, we will make it as by root. So this will be 240. This will also be 240 and A be 240. So current कितना होता है? Current in the resistor 240 by 64. Current in the inductor is 240 upon 40, 6 amperes. Current in the capacitor 240 upon 80, that will give you 3 amperes. So what is the formula for total current in the parallel RLC circuit? Root of IR square plus, like voltage we have done for series RLC, same rule for parallel RLC also. IR square plus IL minus IC, that is a 6 minus 3, that will give you 5 amperes. Similarly, power factor formula is equal to IR upon I, that is 4 by 5, 0.8 amperes. You observe here, IL is more or IC is more here? IL is more, or 1 by XL is greater than 1 by XC. So, IL is more means we should take lag. Why? IL is more than IC. For series, we should take voltage into consideration. Now, what is the average power dissipated? We can take voltage across the resistor, RMS value. You should not take total voltage, but in this case, parallel voltage is same in everywhere. So 240 by root 2 whole square by R is how much? 60, 480 watts. You can also do like this. Current in the resistor RMS value whole square into R. Current in the resistor is how much? 4 by root 2 whole square into 60. In any method, your answer will remain. In any method, your answer will remain same. Okay. I hope it is clear. Don't take total current here. Again, small mistake can be possible is you should not take the total current into consideration. Total current is 5 na. I square into R mat karna. IR you should take. So the next topic of our discussion is average RMS value. So the other important topics we are left over with: average RMS value, power calculation, and resonance. So the next topic of our discussion, average and RMS value. For example, if you have a signal, how do you find average value of the signal is 1 by t integral 0 to t x of t dt, or 1 by 2 pi integral 0 to 2 pi x of t into d omega t. It is nothing but area of the signal over one time period upon the time period. So another one we can say is x RMS. RMS is root of mean of square of the signal. Why do we find RMS value? RMS value is obtained to what we call find the DC equivalent for the AC signal. For example, you have a sinusoidal signal. What is the DC equivalent of the sinusoidal signal? I mean, I will show you that with example, then you'll get a better clarity here. So, for example, you have this kind of signal. What is your x of t here? It is a ramp signal a into t by d. For example, take t equal to 1, a equal to 10, just for understanding purpose. Otherwise, you take anything, no problem. What is your average value? Area over one time period, half into base into height by time period t, that is a by 2, 5, because 10 is taken example. What is XRMS? Integral 0 to t x of t, that is at by t whole square into t. So you will get here a square by 1 by t square. So t square will give you t cube. What is the integration of t square? T cube by 3. That will give you a upon 2. So this is how you find RMS values and average values. So what is the utility of it? Let me give you one example. इससे आपको information मिल पाएगा. For example, I can say for DC, average value equal to RMS. For DC, what is the time period? We should say time period is infinity, we should take. So limit t tends to infinity, we can take is equal to its magnitude. Because DC equivalent of DC is same as the magnitude, right? Its magnitude. For sine or cosine, okay, of for a sinusoidal signal or cosinusoidal signal, कोई भी ले लो, average of any frequency and time period of any frequency and phase, time period is average value equal to 0 for one period, RMS value equal to maximum by root 2. This is the true for any sine wave. We can prove it also mathematically. And also because y average value is 0, integration of 0 to t cos omega t dt is 0. Because integration of cos or sine over one time period, positive half, negative half cancel, okay, 0 ho paega. So, and similarly integration of 0 to t cos omega 1t into cos omega 2t dt is also 0 if omega 1 not equal to omega 2. If दोनों equal है तो cos square आ पाएगा. Then cos square can be written as 1 plus cos 2t by 2. That 1 by 2 will come out in the root as 1 by root 2. That will give you maximum by root 2 as the RMS when you take cos square theta, x square. Okay. Here, now let us find some relations. But what is the meaning of RMS? I will show you. For example, I have 5 cos t. So what is the VRMS? 5 by root 2. Now, if I replace this with a DC signal of 5 by root 2. Okay, both cases, average power dissipated by R is the same. Average power dissipated by the R is same. Why we square it and root it is generally, for example, this is your, suppose this is your output expected. So your output is say reduced by -1 here, increased by +1 here. So when you take normal average, error will be 0, but originally error is not 0. Okay, so that's why if you square it, you can find the error more appropriately. That is the concept of RMS value. Even we use in mean square error, etc. We calculate in the statistics, predictions, etc. That is the reason we take the square in the error. So let's move. I want to give you a few concepts for this. Let's have a discussion of that. For some standard signals, let us try to find average and RMS values. Chalo, just right. So see here. What is XRMS for this signal? A. Now let me find RMS of this signal. Say X2. A and minus A, T by 2 and T. Okay. Square wave signal. I want to find the RMS value. How can I find it? What is the X2 RMS is equal to square root of 1 by T integral 0 to T by 2. What is its value? A square dt. Next, T by 2 to T minus A whole square into dt. So this will give you A because T by 2 T cancels, will get A. My question here is, what is your observation? Sir, X1 is not equal to X2. These two signals are not same. But how RMS is same? How RMS is same? Because after squaring the signals, if you square this signal, what do you get? A square minus A square is also A square. Like this. If you square this signal, you get A square. Got it? So, if x1 is not equal to x2, but x1 square equal to x2 square, then x1 RMS equal to x2 RMS. x2 RMS. You can understand, right? After squaring, because RMS is for the square of the signal. If the signal, I told this example, na, average value will be 0 in this case. Okay. While calculating errors, etc., it will be very much useful. Similarly, if you have this signal, what is XRMS? Integral 0 to T by 2, A square dt. So this will give you A by root 2. Okay, this is 0, T cancels, A square by 2. Root of A square by 2 is A by root 2. So here also one important condition. If signal half rectified, that is area reduced to half, RMS is multiplied by 1 by root 2. So these two shortcuts can help you to solve many questions easily. These two shortcuts can help you to solve many questions easily. You can see here. For example, I have a sine wave with Vm. What is the VRMS? V max by root 2. What is the V average? Ideally 0, but we can also say V average equal to 2Vm by pi per T by 2 time. Okay. Now, if I ask you what is the RMS value of the full rectified signal, directly we can say after squaring both the signals are same. So I need not find its RMS because I know this. I can say blindly my VRMS equal to Vmax by root. And here V average as a standard, better to remember 2Vm by pi. Next, like this, you have some VM, half rectified signal. What is VRMS? It is when signal is half rectified, area reduced by half. Here bottom half or negative half are having equal area, that is required compulsory. Top is a sine wave, bottom is square wave, there you should not apply this logic. So what do you get? 1 by root 2 into Vm by root 2. That will give you Vm upon. Then what is your V average? Half of this, that is Vm by pi. Okay. Got it. Now, similarly, can you tell me the answers for this signal? From the previous, what we call, this is a standard triangular waveform. Previously, I explained for ramp signal, na, what is XRMS is given by A by root 3. Because ramp and this area point of view same. It is just tilted, that's it. So, can you tell me what is the RMS value here? What is the RMS value? In the second case and third case also. Time period doesn't matter, it can be any value because we are integrating up to t and dividing with t. So what is your XRMS here? In this case, square, both of them are same, so a by root 3 on this. Here, what is the RMS value? Half of the signal is removed. Then you get a by root 6 multiplied with 1 by root. That's it. Got it? Clear? Shall we proceed for the next? This is about your average and RMS. In this, only one more model is left over. Say x of t equal to x1 plus x2 plus x3. What is XRMS is given by square root of x1 RMS whole square, x2 RMS whole square plus x3 RMS. Okay, it is true if x1, x2, x3 are 0 average signals, comma, and omega 1 not equal to omega 2 not equal to omega. Okay, except a DC. Except a DC signal, बाकी signals का average value 0 होना पड़ेगा and the individual frequencies same 9 होना पड़ेगा. Say for example, I will take you, say x of t equal to 10 plus 3 root 2 sine 2t plus 10 degrees. So this signal is there. What is x average? Sum of individual averages 10 plus 0 plus 0, it will give you 10. How do you find RMS here? Can you find RMS value here? When multiple signals are added, how do you find RMS value, not individual signal? I will show you here. Okay, you need not try. I will only solve it. Firstly, signals of same frequencies are to be added. So what is 3 root 2 cos 2t plus 45 degrees plus 3 sin 2t? It will be 3 root 2 angle 45 degrees plus 3 angle minus 90 degrees, because sine is, I can write it as minus. So it will give you 3 into cos 43 root 2 into cos 45 is 1 by root 2 plus j 1 by root 2 minus j3. That will give you 3 plus j3 minus j3 is 3 angle 0 degree. So I can write this signal x of t equal to first 10 plus sum of these two will give you 3 cos 2t, 3 angle 0 degrees, 3 cos 2t plus 0 degrees plus 4 cos 3t. After simplifying, then what is your XRMS? Root of individual RMS squares. So if signals are of same, directly don't add them. First you add the same signal frequencies into a single signal, then only you can apply this formula. I'm not going to prove why that happens and all. It takes a lot of time to explain that part. So this is the answer. So shall we proceed for the next question? I hope you understand this. Signals must be of different frequencies with zero average value. Why zero average? Because originally you should find a plus b plus c whole square का integration, a square plus b square plus c square, integration of 2ab 2bc 2ca आएगा. That 2ab 2bc 2ca integration will become 0 when omega are different. Cos omega 1 into cos omega 2 integration will be 0. If same frequency, we cannot use that formula. That is the logic behind this. So now using that, can you try to solve this question? Find RMS value of this signal. If anybody can do this, I am very happy from the class. Anyone give a try and try to solve it and give me the answer. Find the RMS value. Any answer? Okay. One कैसा हो पाएगा? Here, be careful. You can take this signal as plus a DC signal of 1, but this will be wrong analysis. We should not solve like this. Why? Because if you solve in this way, this signal is not having zero average value. Then I should not apply this formula, root of, what is that? Individual RMS whole squares. ये गलत होता है. इसमें क्या करना? जीरो एवरेज वैल्यू है तो ही बिकॉज रूट ऑफ ए प्लस बी होल स्क्वायर ए स्क्वायर प्लस बी स्क्वायर प्लस 2ab का इंटीग्रेशन जीरो होना पड़ेगा. That is possible if you take like this. Take it as plus 1 and minus 1 as one signal. So like this. Okay. Then plus a DC signal of 2. If you take in this fashion, you add them, you get that signal. 2 plus 1 is 3, 2 minus 1 is 1. So here, what is the RMS value is? Maximum value 1 by root 2 whole square plus 2 square. So that will give you 4 plus 1 by 3. That is root 13 by 3. So be careful. Where to apply, where cannot be apply that formula, you should be careful. That's it. So now let's move for the next topic. That is power calculation, complex power calculations. Okay. So let's have a discussion of complex power calculations. So whenever you have a DC, just the power formula is very simple. You have V square into R, V square by R or A square into R. But हमारा पास AC है तो उस केस में Z क्या होता है? R plus R minus JX. Okay. Let us take V and I. Okay. Our source RMS of source voltage and current. Okay. For example, I have like this. This is my V. This is my I connected to a element like this. Okay. So RMS of the source voltage and current, and VR, IR. Okay, you can say resistor V comma I, Vx and Ix, reactance V comma I. Now, real power or active power or true power is the power taken by the resistive part of the load. It is given by VRMS source voltage into IRMS into cos phi. Units are watts. You can also take it as VR RMS only whole square by R. I'm not deriving why RMS and all in a regular class. We generally discuss that average power calculation, everything, but I'm not doing that here into our units. Okay, here because it is just a revision. So this is power taken by the reactive part of the load. The next one is resistive part of the load.
The next part is the power taken by the reactive part of the load is called as imaginary power or reactive power. It is also called as average power also. So previous one, VRMS, IRMS, sin phi, units are volt ampere react. So this can be written as Vx whole square by x or Ix whole square into x. Units are volt ampere react. Originally the units are same because sin phi or cos phi are unitless, dimensionless. But to represent, to differentiate which power it is, we specify like that. Next one is, this is Q. Then apparent power. That is mod S. Apparent power is the mod S root of P square plus Q square. That is VRMS into IRMS. Units are volt ampere. The last one is complex power. The total power. S is given by P plus or minus JQ. Units are volt ampere. Here we take plus for lagging condition and minus for leading condition. ओके ऐसा क्यों ले रहा है? ये सभी चीज तो मैं डिस्कस नहीं कर रहा हूँ क्योंकि कम टाइम पे ज्यादा डिस्कस करना पड़ेगा यहीं पे, राइट? नाउ द एंगल ऑफ एस इज root of, sorry, tan inverse of q by p, which will again give you 5. Okay, so that is about the total power consumed, s equal to plus or this one. Now one important one called as power triangle. Okay, so the power triangle will give you what is your cos phi, p by s, sin phi, q by s, and tan phi, q by p, राइट? सो आपके पास एक पावर है तो दूसरा निकालने के लिए मदद करेगा. नाउ वी विल डिस्कस वन इंपॉर्टेंट कॉल्ड पावर फैक्टर. Power factor is given by active power taken by the load by apparent power. इसको ले सकते p by mod s, which is given by cos. That is the reason your power factor is cos phi. Is it true every time? Means there are some exceptions which we are not discussing, but you should understand the ratio of p by s. Active power taken by the load by apparent power supplied by your source will give you the power factor. But हमने सिर्फ cos phi lagging or leading specify करना, because phi cos theta, cos minus theta, cos theta, both of them will give you the same answer. Now, for example, I have a signal voltage V of t equal to 10 root 2 cos 2t plus 10 degrees, I of t equal to 5 root 2 sin 2t plus 70 degrees. Okay, then I want to find, firstly tell me leading or lagging here. Is it leading or lagging? Is it leading or lagging? Current is leading or lagging? Don't see, sine and cos never compare. First convert this into sine to cos by subtracting 90 degrees. So it will give you 5 root 2 cos 2t minus 20 degrees. So now you take voltage phasor is VRMS angle 10 degrees. Current phasor is 5 angle minus 20 degrees. Z is equal to V by I, 2 angle 30 degrees. You can see current is lagging, right? Current lags behind the voltage. So positive means lag, P plus JQ should. Okay, anyway, now what is your P? VRMS, IRMS, cos phi. What is your Q? VRMS, IRMS, sin phi. What is S? P plus JQ. Volt amperes. Got it? Why plus is taken? Because it is lag. Because I don't have much time, so not solving much number of questions now. Let's have a discussion of the next theoretical topic, resonance. So resonance क्या होता है ना, whenever resonance circuit में when two signals, I mean every body will be having its own natural frequency. Practically you can see these applications like when FM radio is there you tune the signal to one frequency. In free space there are many frequencies, whichever you resonate that you get that particular channel. So here also resonator to generate the heat and heat your microwave devices. Okay, resonance in electric circuit क्यों होता है? Due to presence of energy storing elements both inductor and capacitor. दोनों होता है तो you get the resonance at a particular frequency called resonant frequency. Inductor capacitor क्या करेगा ना? They will be exchanging energy with each other. So because of this exchange of energy oscillations हो पाएगा. So resonance को बहुत सारे applications होता है like tuning circuits, filter design, induction heating, etc. So at resonance क्या होता है ना, मेरा power factor will be 1. This आप याद करना, कोई भी resonant frequency निकालने समय पे please remember that resonance में power factor will be equal to unity. Power factor will be equal to unity. So if you take a series RLC circuit, I'm not analyzing everything here because in the limited amount of time. Okay, so this is series RLC, and similarly you have parallel RLC. Okay. So here, so in the Z, R plus J XL minus XC at omega equal to omega naught. Power factor will be 1. Power factor 1 कब हो पाएगा? Unity power factor के लिए reactance 0 होना पड़ेगा. XL minus XC equal to 0. XL equal to XC or omega naught is equal to 1 by root LC. Here what is the admittance? Parallel overall admittance equal to sum of individual admittances. Okay. At omega equal to omega naught. Here also, if you make J term equal to 0, omega naught equal to 1 by root LC. So if you plot here with respect to omega, resistor is always constant. Inductor reactance will be like this. Capacitor reactance will be like this. is inversely proportional. Okay. So at omega equal to omega naught, both will cancel before omega naught and after omega naught. Before omega naught, capacitor is dominating, so leading power factor. After omega naught, lagging power factor. At omega naught, unity power factor. Okay. And here, at omega equal to omega naught, voltage across the resistor VR equal to I into R. Your Z will be equal to R. And I will be equal to V by Z, that is V by R. Current will reach maximum value. इसलिए इसको बोलते हैं acceptor circuit. Okay. Because resistance will reach minimum value. And voltage across the resistor VR equal to V by R into R, that is V. Voltage across the inductor will be IJXL, that is V by R into omega naught L. It is also written as JQV, where Q is omega naught L by R. VC equal to I into minus JX. So minus J into I is V by R, 1 by omega naught. So minus JQ, where Q is omega naught L by R or 1 by omega naught RC. मैं तो derive नहीं कर रहा हूँ. Voltage in the inductor and capacitor magnified by Q times. इसलिए इसको बोलते हैं voltage magnification circuit. If you add all these three, V equal to V आएगा. ये दोनों cancel हो पाएगा. KVL will be satisfied. No. Same analysis हमने parallel को भी कर सकते हैं. Oh, just a minute. Parallel पे क्या होता है ना? It is omega. This will be 1 by R. This will be 1 upon XL. This will be 1 by XC. So omega naught, omega less than omega naught, omega greater than omega naught. Here you get unity power factor. इसके पहले क्या इंडक्टर ज्यादा हो रहा है. After that capacitor. So lead and lag exactly they are dual to each other. So again here at omega equal to omega naught, y equal to 1 by R, it will reach the minimum value. Z will reach maximum value. Your V equal to IZ is IR. Voltage will reach maximum. It is also called resistor circuit. So at omega equal to omega naught, what is current in the resistor is given by formula V by Z. But what is your Z? Sorry, something wrong. There is some close connection. V by Z, that is V by R. IR in IR by R, which will give you I. Current in the inductor will be V by J XL, that is IR by J omega naught L, which will give you minus JQV. Similarly, current in the capacitor will be plus JQV. Here Q will be different. Q will be omega naught L by R in the series. Parallel पे Q will be R by omega naught L, where Q is called quality factor. At resonance, inductor, capacitor voltages are multiplied by Q here. Currents are multiplied by Q here. Those are called voltage magnification and current magnification for the series and parallel RLC circuits. Similarly, for series RLC circuit, what is your current I? V by Z, that is V by root of R square plus omega L minus 1 by omega C whole square. Got it? So if you observe here, omega equal to 0, omega equal to omega naught, and omega equal to infinity. That is, agar omega vary kiya to, if I have varied my omega from 0 to infinity, my current I will be equal to, in this case, if you substitute omega 0 here, 1 by 0 is infinity, 1 by infinity will be 0. At omega equal to omega naught, this part is gone, current I will be V by R. The current will reach maximum magnitude. Here, current I will be again So if you plot this is the response. So current I will be maximum. This is my current I. So we should take this value where current will reach by root 2. Don't assume this as RMS, 100% wrong. Imax by root 2 is not RMS because Imax and Imax by root 2 is tempting to understand it as a RMS, which is a very wrong conception. It is the maximum, when omega is varied, this is the maximum magnitude you get, and that magnitude by root 2. Why root 2? Because power will be half. Here power will be I max square into R. Here power will be, please understand this max is not maximum and RMS value, maximum magnitude for the any frequency. This is P by 2. Okay. So half power point. These are called half power or minus 3 dB points. Decibel point of it is minus 3 dB. So this is omega L and omega H. Okay. The difference is called bandwidth. So here for series RLC Q equal to omega naught L by R, 1 by omega naught RC, which is 1 by R root of C by L by C. Okay, you can substitute omega naught equal to 1 by root LC, then you will get that. So Q is also given by 1 by 2 times zeta damping factor. It is series RL circuit, Q equal to omega L. Similarly for series RC, Q equal to 1 by omega RC. Okay, their resonance will not be there. Okay, this formula is very important. Now what is bandwidth equal to? Omega H minus omega L. Q is always equal to omega naught by omega H minus omega L. Where omega H minus omega L, this is called bandwidth. Okay, Q is inversely proportional to bandwidth. Q ज़्यादा हुआ तो bandwidth कम हो पाएगा. Then my signal, my curve will come very closer. I can select my required frequency more finitely. इसलिए इसको बोलते, we call it as a selectivity factor. We call it as a selectivity factor. Okay. So what is omega H minus omega L? Omega naught by Q. It is in radians per second. Okay. That is omega naught L by R. Q is omega naught L by R, na? R by L radians per second. So how do you find omega H and omega L is given by plus or minus bandwidth by 2 root of minus bandwidth by just 1 minute. एक minute. I'm sorry. Something, I think I forgot that statement. Yeah, this is plus only. That's why I just got confused. Okay. Similarly, for parallel, we need to plot I. And also here, omega not equal to root of omega h into omega. These formulas are very important. It is just a dual analysis for parallel also. Parallel may you get the dual analysis. You need to plot there for V. Okay. And there Q equal to R by omega naught L and omega naught RC and R times root of C by. One important formula I want to give you, then I'll go for the next topic. RL and L. If you have this circuit, what is the resonant frequency is 1 by root LC, root of RL square minus L by C by RC square minus L by C. We can find resonant frequency by making imaginary part of the impedance equal to 0 or admittance equal to 0. इस case में if RL equal to 0, omega naught equal to 1 by root LC, you take RL 0 here, 1 by root of so if RC equal to 0, omega naught is 1 by root LC. Okay, just substitute that. In this case, if RL RC same, very important. इस केस में मेरा ओमेगा नॉट क्या होता है ना 1 by root LC. And if R square equal to L by C, circuit will be at resonance for any omega. Circuit will be at resonance for any omega. They ask this when you get unity power factor for any omega, imaginary part 0, imaginary part of impedance, admittance 0, all these are same. This is the circuit will have infinite resonant frequencies if R square equal to L by C. So that is about your resonance. Yeah, thank you, Pawan. Even I confused for that plus. That's why I cross-checked it. I should not give you wrong, right? कभी कभी ऐसा भूल गए थे. Sometimes I will also forget the things. So the next topic, magnetically coupled circuits. The last two topics. I don't take much time, just 5-10 minutes I will. So these are due to the mutual inductance mu. These are due to the mutual inductance between the two coils. So this is series connection. Your L equivalent will be L1 plus L2 plus 2N. If the current is opposing, in that case, my L equivalent will be current is leaving from one dot, entering from one dot, then it is L1 plus L2 minus 2N. This one is a parallel connection. L equivalent will be L1 L2 minus M square by L1 plus L2 minus 2N.
If it is opposing, L equivalent will be L1 L2 minus m square by L1 plus L2 plus 2m. So first you have this one is very important, transformer coupling. L1, L2, and between these two, very quickly I am covering this, please understand the available time we have. So this can be written as, it's not opposite, L1 minus m, m, L2 minus m. If it is opposing, just replace opposing, replace m with minus m. Okay. So there is what is the energy stored is equal to half L1 I1 square half L2 I2 square plus m into I1 I2. Okay, this is the energy stored in the transformer. Coefficient of coupling is given by K equal to m by root of L1 L2. K ranges from 0 to 1. M ranges from 0 to root of L1 L2. So transformer can be used for impedance matching. If you have a transformer with turns ratio N1, N2, with current I1 leaving current I2, this is V2, V1. If you connect some load here, ZL, what is the input impedance seen by the transformer is N1 by N2 whole square into ZL. Here always V1 by V2 equal to I2 by I1, V1 I1 equal to V2 I2 because transformer is a reciprocal device, N1 by N2. I2 is the leaving current, please observe. So by adjusting N1, N2, I can adjust my input impedance seen by the transformer. So these are the basic formulas we should know. So lastly, three-phase circuits. इसमें listen here. This is what we call three-phase. Sum of all the three will always give you 0 with 120 degrees phase shift between them. For a three-phase circuit, balanced case phase. So there is one thing we should do. Two important formulas is if it is a star connection and delta connection. Okay, star delta transformations very important. There is a duality between star connection and delta connection that if you understand, remaining all are very easy. I mean, most of the times questions coming from this part only, star and delta. Just 1 minute, I will give you one table and we can leave. In a star connection, your IL is equal to IPH. VL equal to root 3 VPH. VL leads VPH by 30 degrees. Exactly the same thing happens in the reverse thing happens in the delta. In delta, VL equal to VPH. For a positive sequence, we are speaking. IL equal to root 3 IPH. Here lead, right? Here it will be lag. Okay. This is one important thing. Another important thing is the power calculation. So here, power calculation in the three phase. Power calculation P is equal to 3 times VPH into IPH
into cos phi, where phi, hamesha always remember, phi is angle between VPH and IPH. Here instantaneous power and average power both will be same, constant applied. And this is also equal to root 3 VL IL cos phi. बहुत सारे बार questions इससे ही आ रहे हैं. But phi is always angle between VPH and IPH. Okay. Sometimes we can also say S equal to 3 times VPH into IPH conjugate ले सकते हैं. But don't take here root 3 into VL into IL conjugate. ये गलत है. You should not take angle. Conjugate is to subtract the angle only. That should not be taken for this one. That's it from my side. We will meet with PYQ sessions tomorrow. Tomorrow means day after tomorrow. So in the given time, I have covered elaborately everything. These notes will be more than enough for every revision also. So kindly guys, up to now, if you have not yet subscribed to this channel, subscribe it, like the session and share, utilize this, whatever the discussion, it will be very much help. Okay, thank you guys.